Okay, so hello and welcome everyone to our webinar Behind the Scenes of Machine Learning. My name is Kathrin and I'm one of the data scientists at Knime in the evangelism team. The second part of this webinar is going to be run by one of my colleagues, who's Rosaria, and she is the head of our evangelism team. Before we start with the webinar, you can ask questions by using the Q&A section, where you can post your questions. You have there also the option to upvote your favorite questions, and then we will answer your questions either right away in the Q&A section, or we will answer them in the end of this webinar live. This session is recorded and will be also available on YouTube afterwards. Where can you actually ask your questions? To ask your question or to type your question, you can just click on the button, on the Q&A button in the toolbar of Zoom on the bottom. Okay, so what do we want to talk about today? So we will start with talking about the different ways of how a machine learning algorithm can learn. We want to focus on supervised and unsupervised learning. And then we will talk about some of the commonly used algorithms, and we want to give you an idea of how these algorithms work. So you know, if you change certain parameter settings for an algorithm, what that actually means. And therefore, we will start with different algorithms for solving classification problems, and we will talk in particular about the decision tree algorithm and the random forest algorithm. Then we will talk about some clustering algorithms, or Rosaria is going to talk about some clustering algorithms, the k-means algorithm and the DBSCAN algorithm. And then we conclude with the a priori algorithm for recommendation engines. So let's start with the different ways of learning. So when we train or when we learn an algorithm, the goal is always to have then a model that we can use to make some predictions. This means in the end, the goal is to have a model into which we can feed some data, which is often called either input features, input attributes, or independent variables, which then generates for us some output, which is often called either class, label, target, or dependent variable. The model itself is then normally a function that depends on one hand on our input features and on the other hand on some parameters beta. And then we always feed into this mapping functions our parameters beta as well as the input features, and this gives us then the output. And these input or these beta parameters are often called model parameters, and some algorithms have more parameters, some algorithms have less parameters, but normally we have more than one, so this is actually a vector of parameters where we have then model parameters beta 1 to beta n. And when we now use a learning algorithm to train our model, what we actually are looking for are these model parameters. So normally when we train an algorithm, the learning algorithm adjusts these model parameters beta throughout a number of iterations by either maximizing or minimizing a likelihood function or an error function, so that if we then afterwards apply our trained model, that when we show it or when we feed some input features into the model, it actually generates the correct output for us. And now there are different ways of how we can learn an algorithm, how the algorithm can learn. And the different algorithms can be grouped in three groups into supervised learning algorithms, unsupervised learning algorithms, and semi-supervised learning algorithms. And we want to concentrate today on supervised learning algorithms and some unsupervised learning algorithms. So let's start by finding out what are supervised learning algorithms. So whenever we want to apply an algorithm that belongs to the class of supervised learning algorithms, then we need something that is called a labeled data set. This means we need a data set where we have on one hand our input features and in addition also our class information. So we need the input and the output together. And then, for example, if we have two samples, we can represent them in the feature space in the scatter plot, where we have one sample that belongs to our class represented by yellow, where we have a small value for one of the input features, x1, and a larger value for the second input feature, and one sample that belongs to class gray, where it's the other way around. So we have a high value for the feature x1 and a low value for the feature x2. And these input features could be then, for example, in case of customer data, the age or the money a customer spent or the number of calls a customer made, and so on. And the different class values could be, for example, churn, visual remain, or sunny, visual cloudy, and so on. To train now a model, it is not sufficient to have just 2 data samples, but we actually need a training set with many examples. This means we need quite often the input features and in addition also the class information. And when we then train our algorithm using a supervised learning algorithm, then the model learns based on the examples of the training set to always produce the right value for y for an input vector x. So we show it the input features, and then it should create our output value correctly, either yellow or gray in our case. And the model for this simple example could look then like this, which separates our 2 classes from each other nicely. There are kind of 2 groups of supervised learning algorithms. One where the target value has different nominal values, like for example, churn and remain, or the hair color, brown, blonde, and red. But on the other hand, there are also algorithms where we don't want to predict a class value, but where we want to predict a numerical value. So that these are then the algorithms that we can use to solve regression problems. So we have supervised learning algorithms on one hand to solve classification problems where we want to predict a class value. And on the other hand, also supervised learning algorithms where we want to predict a numerical value, like for example, the amount spent for certain in a shop or the temperature on the next day or so on. Whenever we use an algorithm that belongs to the class of supervised learning, we kind of follow the same steps. Because what we want to do once we trained our algorithm is we also want to evaluate how good our model performs. And therefore, the first step is always to take our original labeled data set, so where we have the input information and the class information, and we partition this data set into 2 subsets, one subset for training and the other one for testing. And then we use the training set to actually train our model. And then we use the test set to apply our trained model. And then we are here in the situation where we have on one hand the true values and on the other hand the predicted values. So we can then evaluate how often were our predictions correct and how often were our predictions wrong. But quite often we are not in the situation where we have a labeled data set. So quite often we are actually in the situation where we have only the input data, but the target value is not available. So we don't have this class information. And in this situation, we can use unsupervised learning algorithms. So in this case, we have just a training set with many examples where we have the input features. And in supervised learning, the goal of the algorithm is to train a model that groups similar examples together. So we are now looking for groups in our data set where the samples are similar, so where we have similar values which are close to each other. And here the model could, for example, group our training set into 3 groups. And then if we have new data samples, always assign it to the closest group. I now want to continue with the decision tree algorithm. And the decision tree algorithm is one algorithm that belongs to the class of supervised learning algorithms. And it's actually available on one hand for classification problems and on the other hand also for regression problems where we want to predict a numerical value. Today, I only want to focus on the decision tree algorithm for classification problems. This means for problems where your target value is nominal, where you have different classes. One of the things I like to do in my free time is to go sailing. And imagine my colleagues have now collected some data about my sailing habits, and they want to train a model which they can use to predict on a new day whether I go sailing or not. This means we have a data set like the one here on the left, where we have 4 input features, the outlook, wind, and temperature, and whether the boat was in the winter storage or not. And in addition, we have also the target information, where we have 2 different classes, yes and no. Then the goal of the decision tree algorithm is to find a decision tree like the one here on the right. And how so that my colleagues can apply this decision tree then on a new day. And how the decision tree algorithm works, or a decision tree works, is then that it always splits our data set into multiple subsets, always based on the values in one of our input features. For example, here, this decision tree, in this decision tree, the decision tree algorithm decided to use as the first splitting feature, the input feature winter storage. And then it created two subsets and two branches. One subset where we have all the samples, all the rows, where we have yes in the column storage. And on the other hand, here, a second subset where we have all the samples where the boat was not in the winter storage. And then we have here a subset where we see that we have only samples for the class no. And this is something that we call a pure subset. We have only samples left for one class. And therefore, the decision tree algorithm produced a so-called tree leaf. Here, we don't have a pure subset. We see we have still samples in the subset for both classes, saying yes and no. And therefore, the algorithm decided to continue and take the next feature and split based, in this case, on the feature wind, to check whether the wind speed was above or below 4 before. And then the decision tree algorithm continues, always selecting one of the features and splitting the data set based on their values until we only have pure subsets or the subsets are sufficiently small. But actually the tree that we see here is not the only possible tree. So instead of using in the first split the input feature storage, the decision tree algorithm could have also used the input feature outlook. So how does the decision tree algorithm decide which feature to use when to split our data set? And the goal of the decision tree algorithm is to always use the feature to split, which leads to the purest subsets afterwards. And the question now is, how can we measure which input feature actually leads to the split with the purest subsets afterwards? And there are different possible split criterions, and one of them is the gain ratio. And the gain ratio is a split criterion that is based on entropy, which is a measure for information or uncertainty. The entropy for a data set can be calculated by checking the probabilities for the different classes. And then it's calculated by the negative sum of the probabilities for the different classes, multiplied always with a logarithm of the probabilities for the different classes. Let's have a look at these two subsets where the two different classes are represented either by red crosses or blue dots. For the data set on the left, the probability for the class represented by the red crosses would be 7 divided by 13, because we have 7 red crosses in our data set and 13 samples in total. And the probability for the class represented by blue dots would be 6 divided by 13. On the other hand, for the data set on the right, where we have only red crosses, if we pick one sample there randomly, we would certainly pick a data sample which is represented by red cross. Therefore, the probability for red crosses is 1. And because we don't have any blue dots, the probability for the blue dots is 0. If we now apply the formula for the entropy for these two probability distributions, then we see that the entropy for the data set on the left is quite high, which is 0.995. And the entropy for this pure data set is actually 0. What is important to know is that the entropy is always, for a binary classification problem, is always between 0 and 1. So 0 is the lowest entropy value that we can have, and 1 would be the highest. And we now use this idea of entropy to find the best possible split criterion, because we know the purer our subset is, the lower our entropy is. And what the decision tree algorithm do is it then calculates the entropy always before a split and the entropy after a split. How we can calculate the entropy before the split, that's something we know already. We can just apply the formula from the slide before. How can we calculate the entropy after the split? Where we have more than one data set. So what we do there is we calculate the entropy for each subset after the split, and we multiply it by a weight, which is the proportion of the data set before the split. So in this case, we have 6 samples left in our subset, and therefore the weight is 6 divided by 13, because we have 13 samples in total before the split. And then we now know the lower the the purer our subsets, the lower the entropy is. This means if we have here pure subsets, then the entropy would be always 0. This means we now take as next splitting feature always the feature with the highest difference between the entropy before and after the split, because if we have pure subsets or nearly pure subsets here, the entropy values will be lower, and therefore this difference gets bigger the purer the subsets are after the split. As I said, one of the possible split criterions is actually gain ratio. I now talked about the gain in information, and the gain, using the gain as a possible split criterion has one problem, because it favors features with many different values. What does this mean? So imagine we have in our sailing data set from the beginning one additional input feature, which is the date. And if we now make a split, then we have for each day another date. If we now would split based on the date, then we would get one branch for each sample. And therefore, the gain in information would be maximum, because the entropy for each subset would be 0, but actually there's always only one sample in there. So this wouldn't be a good split, even though the gain is really high. So it really means if we use the gain, we favor features with many different values. And the solution to this problem is the gain ratio, where we use the gain, but in addition, we divide the gain by something that is called the split info, which is calculated as the sum of these different weights multiplied by the logarithm of them. And if we have here now many different subsets, then we have here many values and therefore a higher value, and then this gain ratio becomes smaller. Another possible split criterion that is used in the decision tree algorithm sometimes is the Gini index, which is based on the Gini impurity. And to calculate the Gini impurity, we again need the probabilities for the different classes. And the Gini impurity is then calculated by 1 minus always the probability of the different classes squared. The Gini index is then calculated by calculating the Gini impurity for the different subsets after the split, and by multiplying them again with the proportion of the data set compared to before the split, which are the same weights then in the gain ratio. And here we use then as next splitting feature, the feature with the lowest Gini index. If we now use the decision tree algorithm, it always splits our data set based on one of the input features. But the question now is, when should the decision tree algorithm stop? And I said in the beginning, it continues taking always one of the input features and splitting based on this one until we either have only pure subsets or the subsets are sufficiently small. Let's have a look at an example whether it's always better, the deeper the tree, the better the tree, whether that's always true. Here we have now a data set where we have our two classes, again represented by the blue dots and the red crosses, depending on two of our input features, wind and temperature. And we say the filled out dots and red crosses are actually the samples of our training set, and the not filled out blue dots and red crosses are our test set. Our decision tree algorithm starts now. It could say it sees only the training set and not the test set, of course. And then it would select one of our input features to make the first split, for example, first wind, and to check whether the wind is above or below 4 before, because then we have already two nearly pure subsets. And then it continues to check, for example, the temperature for the values where we have wind below 4, to check whether the temperature, or to split whether the temperature is above or below 25. And then we have here one pure subset and one nearly pure subset. And then maybe we make two more splits, also for the values where the wind speed is above 4 before. And then we see here now all samples are, or nearly all samples in our training set are already classified correctly. But now we can continue our tree to kind of grow the tree in a way that we also extract this single blue dot here by making 3 more splits. And the question now is, this tree which separates also, or which classifies this blue dot here correctly in our training set, better than this shorter tree? And For our training set, this is correct because it classifies also this other sample correctly. But what happens if I add now again our test set? Then we see by adding these 3 more splits to our tree, this actually leads to more misclassifications in our test set. So this means this deeper tree performs really good on our training set, but it kind of learned details of our training set and therefore doesn't generalize to our test set anymore and also not to new data. And this problem of training a model or an algorithm too well, so that it includes also details and noise, is known as overfitting. And the goal is always to train an algorithm that actually is also able to generalize to our training test set and then to new data. Therefore, we want to try to avoid overfitting. But first, kind of summarizing, what does overfitting mean? Overfitting means that we train a model that fits the training data too well, including noise and details. And we train it that well that it has actually a negative impact on the model's ability to generalize. The opposite of overfitting is underfitting. There we would then train a model that can neither model the training data nor generalize on new data. And for example, if we have training and test data, which is distributed like here on the right, and I try to fit a linear regression, and I have a model like this, then this would be a model that does not fit my training data and not my test data, and therefore would be a model that underfits. But a model like this one here in the middle would be a nice model that fits my training data and also my test data. So how can we now control in a decision tree that we don't overfit so that we have a tree that generalizes also to new data? That's something we can do in a case of the decision tree algorithm by controlling the depth of the tree. And here we have 2 options in the decision tree algorithm. We can use on one hand early stopping, and on the other hand, we can use pruning. The idea of early stopping is to define a minimum size for the tree leaves before we start training our tree. This means we define, for example, the minimum size for the tree leaves as 5. And as soon as we have a subset that has only 5 or less samples, then the algorithm creates a leaf and takes the majority class as the class for this subset. The idea of pruning, on the other hand, is to grow first a really, really deep tree and then cut afterwards branches that seem as a result of overfitting. And there we have 2 techniques implemented in Knime Analytics platform. On one hand, we can use reduced error pruning, and on the other hand, we can use the minimum description length pruning. The idea of reduced error pruning is to start at a tree leaf and then always take the tree node, which is above this tree leaf, replace this tree split with the majority class and see whether the accuracy doesn't decrease. And if the accuracy doesn't decrease, we go for this shorter tree. The idea of minimum description length pruning, on the other hand, is that we check how many bits do we need to encode all samples by encoding the tree and the misclassified ones. And if a shorter tree has a shorter description length or a smaller description length, then we take the shorter tree. Once we trained then our algorithm, we can apply our algorithm, for example, to the test set or to our new incoming data. Sometimes we have then the problem that our decision tree actually predicts a missing value. And this is because of the no true child strategy. So we see here again the training or the data set from my sailing example from the beginning, where we use the upper part for training and the lower part for testing. And if we look now into the outlook input feature, we see here we have the values sunny and rain in our training set. So if the decision tree algorithms decides to split based on the feature outlook, then it would create 2 tree branches, 2 subsets, one for the samples with sunny and one with rain. If I now go into my testing set, I see that I have here an additional possible value, which is overcast. And now if we now apply this decision tree, then the algorithm or the model actually doesn't know what it should do if the outlook is not sunny or rain, but overcast. And there we have then 2 options. We can either say if there is no value matching or no branch matching in a decision tree split, then we either predict a missing value. That would be the setting option for return null prediction. Or we can also return the last prediction. Then we would just take the majority class from the subset before the split. Next, I want to talk a little bit about evaluation matrices for classification models. But why do we actually need to evaluate our model? First of all, of course, we have to evaluate our model to obtain whether the model performs as well as we expected. And on the other hand, I talked already about different configuration options. So for example, we can have different split criterions, or we can use minimum description length pruning or not, or we can use early stopping and define a minimum number of samples for each tree, for each leaf. So you see there are different configuration options, and if we want to compare different setting options to kind of find the best model, then we do need to evaluate our models for different setting options. And there are different options how you can evaluate your model. What is, for example, whether your data set is unbalanced or whether you have a balanced data set, whether you have a classification problem or you have a regression problem, and so on. One of the options to evaluate your model is by having a look at the overall accuracy. And the overall accuracy tells you the proportion of the correct classified samples in your test set. This means to calculate the overall accuracy, we check how often was our predictions correct for the test set, and we divide it by all the samples that we have in our test set. The overall accuracy is really easy to calculate, but it has some downsides because it only considers the performance in general, but not for the different classes. And therefore, it is not informative when the class distribution is unbalanced. This means if we have many samples for one class and not many samples for another class, then the overall accuracy is not a good evaluation, not a good performance measure. Another way of checking how good your model performs is by having a look at the confusion matrix. And the confusion matrix tells us how often each class was predicted correctly and how often each class was predicted wrong. And therefore, we have always in the rows the values for these samples for the true classes, and in the columns, the values for the predicted classes. So how many samples were predicted with the different class values. So in this case here for the sailing example, we would have in our test set 25 samples where we have the class yes, and we have 350 samples which belong to class no. And out of them, 22 were predicted correctly. And 3 of the samples for the class yes were actually predicted wrong. So this means on the main diagonal, we have always the number of samples that were predicted correctly. And on the off diagonal, we have the misclassified samples. And we can use these values now, of course, or the confusion matrix or the values in the confusion matrix also to calculate the accuracy. And in this case, this would lead to an accuracy of 96%. And for this confusion matrix, we see that the model kind of learned in a good way to predict the class yes and also the class no. On the other hand, if I have a model that leads to a confusion matrix like this one, I would see that even though the accuracy is still really high with 93%, this is actually not a good model because this model predicts most of the time no. And just because our data was so highly unbalanced, because we have much more samples for the class no, the accuracy is still high, but actually the model is not good because it just predicts most of the time no. Another measure to evaluate classification problems is the Cohen's kappa. And if I calculate the Cohen's kappa for the two models represented by these two confusion matrices, then we see that the Cohen's kappa is actually an evaluation matrix that is much more sensitive in case you have unbalanced data sets. Because here you see the Cohen's kappa, which is always between 0 and 1, is quite high for the left example, but really low to, in the example that we see here on the right, where we have our not good performing model, which predicts most of the time no. The values in the confusion matrix have also some dedicated names, which are true positive, true negative, false negative, and false positive, which you might have heard before. And what we do here is we arbitrarily define one of the class values always as positive and the remaining class as negative. And then the cases or the number of samples where we predicted positive and the actual class is positive are called then true positives. And the number of samples where the actual class and the predicted class is negative is called true negative. The number of samples which were predicted as positive but which are actually negative are called false positives. And the number of samples which are actually positive but were predicted as negative are then called false negative. And these false positive, true positive, false negative, and false positive values are also actually used to calculate a lot of other evaluation metrics like the overall accuracy or the true positive rate and the false positive. Now I would like to show you in a short demo how you can actually train a classification model in Knime Analytics platform using the decision tree algorithm. This means we want to train now a model into which we can feed some customer information and which then predicts for us whether this is a customer that is likely going to churn or no churn. And the workflow I'm using, you can find also on the Knime Hub. And one of my colleagues will post this link also in the Q&A section or in the chat. So let's now switch to Knime Analytics platform. So here I have started already building a workflow where we read in customer information from a telecommunication customer. So we have here on one hand in an Excel file some calls data of the different customers. You can open this data set. For example, we know how many calls the customer, how many day calls this customer did, how many evening calls the customer did. And in addition, we have also the phone number. And then we have a second data set where we have the contract information for all customers and also the phone number. And here we have in addition also the information whether the customer churned or he did not churn. And what we do here in the pre-processing part is that we combine this data together and we do some type conversion where we convert the churn from data type number to string. Now, the first thing I want to do is I want to create a training set and a test set so that I can evaluate my model afterwards. And that's something I can do in Knime with the partitioning node. So I can look for the partitioning node in the node repository. And if I go into the configuration window, I can choose now the size for the first partition. So for my how much data I want to use in my training set. And then here normally data scientists use between 70 and 80% of the full data set for training. I will use now 70% of my data set for training. And here in the lower part, I can define how I actually want to create my two subsets. And I want to ensure that I have in my training set and in my test set enough samples for both classes, churn and no churn. And that's why I go for the stratified sampling based on the column churn. And then I can execute the partitioning node, where I have now here at the first output port my training set, and at the lower output port my test set. If I now want to train a decision tree in Knime, then I need the decision tree learner node. So I can drag and drop the decision tree learner node into the workflow editor and connect it with my training set. If I go now into the configuration window, you will find all the setting options which I described in my presentation. First of all, we have to decide in which column is actually our class column. So where do we have our class information? In our case, this is the column churn. Then, for example, here we can select between different quality measures or splitting criterion, in particular the Gini index and gain ratio. And we can decide here by using this checkbox whether we want to use the reduced error pruning to avoid overfitting or the MDL pruning. Once you define, and here's also this setting option for the early stopping where you can define the minimum number of records per node. If you're happy with the setting options for the algorithm, you can click OK and execute the node. And what is really nice with the decision tree algorithm is that you can actually also inspect the tree afterwards by right-clicking and saying view decision tree view. And then you can go through the whole tree and see that, for example, it first used the customer service calls and then the day charge and so on. Next, we want to apply then our decision tree to our test set, and that's something we can do with the decision tree predictor node. So I use the decision tree predictor node, feed into this node on one hand my model and on the other hand the test set. and then I can execute this node. At the output port, I have now one additional column, which gives me the predicted values. And now I have here in one data set, on one hand, the true values, and on the other hand, the predicted values. And now I can evaluate how often were my predictions correctly and wrong by using the scorer node. And here in the configuration window, I only have to define where I have my true values and where I have my predicted values. And if I execute and open the view now, I see on one hand here the accuracy of my model, which is 90%. And I see here on the top the confusion metrics and also the Cohen's kappa, which I showed you in my slides. Okay, now you know how you can train a decision tree in Knime and how you can evaluate it. So let's see what kind of other algorithms we can train. And one other option is to use the random forest algorithm. The random forest algorithm belongs to the class of tree ensemble models. And the general idea of ensemble models is to take advantage of the wisdom of the crowd. This means when we train an ensemble model, we don't train only one model, but we train many models, and then we combine the predictions by predicting then the class which was predicted most often. And this leads in general to more accurate and more robust models. A downside is that these models are harder to evaluate because I now showed you how nice it is to kind of check the decision tree. Here we would have then not only one tree, but we would have multiple trees. So it's not so easy to interpret anymore. If we now want to train multiple trees and not only one tree, then we also have to kind of create multiple training sets, because if we use always the same training set, then we would also always get the same decision tree model. So the idea of random forest, or the random forest uses therefore the idea of bagging to create multiple training sets. And we create for each tree or for each model one training set by sampling uniformly with replacement from the standard training set, so that we have then multiple different training sets and we always train a decision tree on another training set. What does it mean to sample uniformly with replacement? So how does bagging or bootstrap aggregating work? So here I have now a little example. Let's say here we have on the left our full training set, and our goal is to have a sample training set which has the same size. If we now sample uniformly with replacement, then we would always pick one of the rows available in our full training set, and we replace it back so we can still also sample one more time row 6 or row 3, which we have already in our training set. So for example, we would pick first row 3, then row 6, row 1, and then again row 3, then maybe row 5, row 6, and then row 1. So we can have some of the data samples actually multiple times in our data set if we use bagging, but our data sets, all the different data sets for the different decision trees will be a bit different. But if we use bagging, we have an extra benefit, which is the out-of-bag estimation, because we now don't use all rows to train our decision tree or to train our tree, and therefore we can always use the samples that we didn't use during training to evaluate our model already on a part of the training set. And this is called the out-of-bag estimates. So we apply always the samples that were not used for training this tree to make already some predictions. And here we see now, for example, the output table created by the random forest learner node in Knime, which tells us on one hand how many trees were trained where this sample was not used. For example, for the first row, 35 models. And we can apply these 35 trees already to this sample, this row of the training set. And we get here already some predictions and compare already on these values whether the predictions were correct or not. The random forest algorithm now uses this idea of bagging to create the different subsets. But when we train this tree, when we apply the random forest to train our trees, we add an extra element of randomization, because whenever the algorithm kind of selects between the input features, it doesn't see all the different input features, but it always only sees a subset of the input features. Typically only the square root of the number of input features that you have in your training set. And this random forest algorithm then tends to be very robust with regard to overfitting. And this random forest algorithm has now also much more setting options compared to the decision tree, because we still have the same settings like for the decision tree for a single tree, but now we can also select how many trees we want to train, for example. And if you have many settings in an algorithm and you want to find the best settings, then you can either try out different settings manually and always evaluate your model and check how good your model performs. Or you can do this also automatically in Knime Analytics platform by using the parameter optimization loop. And here we have done a parameter optimization loop start and end node. And in the start node, you can define the different parameters that you want to test. And the loop end node then collects the performance for all the different setting options. So let's see now whether we can actually improve our churn prediction model by using a random forest, so by training multiple decision trees compared to just a single decision tree we just trained. So what I will do now is I will use again my training set and my test set, and instead of training a decision tree, I will train a random forest using the random forest learner node. So I first look for the random forest learner node in the node repository. In the configuration window, I again have to define where is my target column, so where do I have my class information. I can here define which features which of the columns in the input data I actually want to use as input features. I have here the option to select between different split criterions, the information gain ratio, and the Gini index I introduced in the decision tree algorithm. And we have here also the option to define how many trees we actually want to train in our random forest and how deep each tree is allowed to be. And then I can execute the random forest learner node to apply the random forest algorithm. And if I open here the view, you can actually have a look at all the different 100 trees which were just trained by this random forest learner. And you see, in addition to the model output port, this node has also some data output ports where you get, for example, the out-of-bag predictions, which I just mentioned. Let's now apply the random forest model to our test set so we can see how good it performs. And I will execute it as well. And I will also use a scorer node to evaluate the model. And again, that's something I didn't want. So again, I define where I have my true values, churn, and where I have my predicted values. And if I execute the scorer node now and I open the view, I see that I have now a model that has a higher accuracy. Remember, our decision tree had an accuracy of 90-something%, and now we have an accuracy of 93%. So actually, our random forest performs better, so the many trees perform better than the single tree. And this brings me to the end of the part about classification problems. And with this, I will hand over to Rosaria, who is going to talk about clustering problems.
Okay.
Rosaria?
You need to unshare.
Ah, sorry.
Okay. So hi, I'm Rosaria, and I'm going to talk about clustering. So I'm going to stop answering questions. Okay, so we have talked about, until now, we have talked mainly about supervised classification. So we already knew we had a data set, and each pattern, each example in the data set had an answer. So we knew exactly the model we wanted to implement because we knew exactly what the association between the example, the input in the example, and the output in the example was supposed to be. In the clustering procedures, we don't have this. So we have a bunch of data, but they are unlabeled. So we don't know what the correct output will be. This kind of learning is called unsupervised. We said that already. And the whole goal of cluster analysis is to identify finite set of groups, we call them clusters, and we want these groups to have these groups to contain objects, and objects in the same clusters have to be as similar as possible, and objects in different clusters have to be as dissimilar as possible. So that's what we want to do. We want to group together our data in these clusters, and we want to have the most similar data to end up in the same cluster. So clusters may have different sizes depending on the structure on the algorithm that we are using, the structure that we are forcing the cluster to have, and something like that. So we can have spherical clusters, we can have weird shaped clusters and stuff like that, big clusters, small clusters, clusters very much populated and clusters with not that many points inside, and so on. We can have clusters that form a hierarchy. So first we have a bigger cluster which can be separated in many clusters, and then we can have clusters that may be overlapping or may be disjoint. So here you see some examples of all these clusters I'm talking about: spherical clusters, overlapping clusters, hierarchy of clusters, and then here weirdly shaped clusters. Okay, so let's talk. I'm going to explain only two of the algorithms that are available for clustering. Of course, there are many more, but those are the most commonly used algorithms when it comes about clustering. If you want to know more, of course, you can always read more about other algorithms. So the most used, the classical, most used, the most simple to use algorithm in clustering is the k-means algorithm. The k-means algorithm is implemented in 4 steps. We decide we want to build k clusters. Okay, so we decide that at the beginning. Then we partition our data set in k non-empty subsets. And then for these k non-empty subsets, we calculate the representative points. They are called centroids in the k-means. The centroids are calculated as the average point of all the points in the cluster. At this point, we examine all the points in the data set, and we assign each object to the cluster which has the nearest centroid. So we calculate the distance of all the data points to all the centroids of the clusters, and then we reassign the data point to the closest cluster, to the cluster with the closest centroid. At this point, then we have a new partition because we have performed a reassignment, and then we recalculate the centroids for the current partition of clusters, and then we start again. We recalculate the centroids, we recalculate all the distances of the centroids to each data point, we perform the reassignment, and so on and so on. Until we repeat all these steps until the centroids update and the assignment of the data points to the cluster doesn't change much anymore. The node in Knime that implements the k-means algorithm is the k-means. So important, there are 3 parameters in the k-means. One is the number k of clusters that we want to build and has to be decided before. Then we have the centroids. By default, in the k-means algorithm, they are calculated as the average of the points in the cluster. And then the nearest centroid, which implies the usage of a distance, and in the k-means algorithm is the Euclidean distance. Okay, so those are the choices for the k-means algorithm. Let's see what happens. This is our original data set. We decided to partition the data like that randomly, and we decided that we have this cluster here and this cluster here. So let's perform the step number 2, and then let's calculate the centroids of these partitions, of this cluster partition. So here, there are the centroids. As you see, those are not physical points. They are just the average point, the average abstract point of the points in the cluster. After that, we perform the reassignment. So we take each data point of the data set, we calculate the distance to the 2 centroids, and we decide which one is the closest, and we perform the reassignment of the data point. So here you see there is the light blue cluster and the dark blue cluster, and then here you can see that this dark blue point has become light, and the opposite here, right? So because this one was closer, these 2 points was closer to the centroid of the other cluster, so that's why they got reassigned to the previous cluster. So now let's calculate the new centroids, and then we end up with something like that, and so on. And we repeat and we repeat and we repeat. I would like to make you notice something. When we passed from this original cluster partition to this second iteration cluster partition, we can see that the clusters have become more spherical, right? And the K-means has this feature, this particularity of building spherical clusters. So let's see, let's comment a bit on the K-means algorithm. First of all, it's quite easy. It took 2 slides to explain it, so it can't be that complicated. It's a very simple implementation. It's the calculation of all the distances, calculation of all the centroids, and repeating and repeating. So it's efficient, it's simple, it's easy to understand. The problem is that it often terminates at a local optimum, so it doesn't collect the data. It doesn't separate them in the best optimal way, but in a local acceptable way. It is applicable only to numerical data because you have to calculate all these distances and you have to calculate the average point, so the categorical data are not considered for the K-means algorithm. You can, of course, always do some kind of binning to move the numerical data, the categorical data into the numerical data. You can do some kind of transformation, but by principle, it applies only to numerical data. The K has to be defined in advance. We never know how many clusters are the optimum number of clusters. Since it builds these spherical clusters and it always wants to include all the data points in one cluster, it ends up to include also noisy and outlier data. Including noise and outlier data can disturb the regularity of a cluster. So it's not very good at handling noisy and outliers in the data. It's also not suitable to discover clusters with non-convex shapes. You have seen that it tends to form spherical clusters. So one problem is then is the one about the outliers or the noise. So let's suppose that I have a nice spherical cluster and then I have an outlier far, far away, right? At this point, I'm going to have that the centroid of this cluster is not going to be in the place of biggest density of the cluster, but it's going to be in some strange position between the outlier and the other points. So this kind of distorts the distribution of the data when we want to assign them to a cluster. So one solution for that is the K-medoids. Instead of taking the average value of the objects in the cluster, then we take a real point, one existing point, and exactly the one that is most centrally located inside the cluster. So the advantage is that we are not going to build an abstract point that somehow is too close to the outlier and not too close to the other high density points. So it's going to be some real points, maybe located at the border of the cluster, but still in the high density part of the cluster. The node that implements the K-medoids is the K-medoids node. Okay, so another parameter that I was talking about is the distance functions. We said K, we said the way to represent to calculate the centroids, and then we cut the way to calculate how close a data point is to a centroid. So those are the distance functions. We have talked about Euclidean functions, that's the default, but we can use also a number of many different functions. Of course, using different distance function allows to build differently shaped clusters. Okay, so here there are some of the most commonly used distance functions. For example, if I use as a distance function, I can also take into account some input features more than other input features. So let's suppose that we have a data set with only 3 data points. Those are vehicles, a red Ferrari, a green Porsche, and a red Bobby car. The Bobby car is the toy car for kids. So let's see how we might want to cluster those. If we decide to use a distance function based on maximum speed, then in this case, the Ferrari and the Porsche, they would end up in the same cluster, and the Bobby car would be alone in another cluster. But if we want to cluster based on color, then we would have the first cluster where we have the Ferrari and the Bobby car, and the second cluster where we have the Porsche. So the way that you use the distance affects the kind of distance you use affects the shape of the clusters. Also, the features that you use for your distance calculation also affects the shape of the clusters. So here I would like to remind you that every time that there is a distance involved in the calculation, in the implementation of an algorithm, remember that you have to normalize the data. Otherwise, you are going to end up with different data with features with different ranges, and the feature with a much bigger, larger range is going to dominate the other features with a smaller range in the calculation of the distance. And then, of course, then the whole clustering procedure is going to be dominated by the feature with the largest range. Okay, so another clustering procedure is the DBSCAN. The DBSCAN is a density-based clustering algorithm and defines 5 types of points in a data set. So it is not purely based on distance, but it's also based on density. So the first points that it takes into account are the core points. We specify a radius epsilon, and then we take one point, we draw the circle with radius epsilon around this point. If inside this circle we end up having at least a minimum number of neighbors, then this is defined as a core point. So the core points are the points with at least a minimum number of neighbors within a specified radius epsilon. So the core points are the most important points in this algorithm. Then you have the directly density reachable points. Those are the points that fall within this distance epsilon, this specified distance epsilon from a core point. Then you have the density reachable points, and those are those points that don't fall close enough to a core point, so they are not in this circle of radius epsilon, but they are reachable from a core point through a chain of directly density reachable points. So if you can reach them via this epsilon distance through a chain of directly density reachable points, those are the density reachable points. Then we have the border points. The border points are those points that are located within this distance epsilon from a core point, but they have less than the minimum specified number of neighbors. And then there are the noise points. They are all other points. So they are neither core points, they are nor border points, so they are anything else that is noise, exactly. So the clusters are then built by joining core and density reachable points one after the other. So I'm going to show you how. So this is an example. The T is a core point. You see the circle with radius epsilon, and then the minimum number of neighbor points is in there. Let's suppose that the minimum number is 4. It has 5. Perfect. It's a core point. S is a border point. So it's a point that is, it's not a core point because it doesn't have the minimum number of points inside the circle, but it's reachable from the core point T. And then N is the noise point because it's not close to anything. It cannot be reached by anything. It's just alone in its own epsilon circle. Here again, we have the T core point. We have the Z, which is the directly density reachable point because it's inside the circle of radius epsilon from T. And then S, which is the density reachable point because it's reachable. It's not close to T via the radius epsilon, but it's reachable via a chain of directly reachable points, so via Z. So yeah, those are the different types of points considered in the DBSCAN algorithm. Okay. So now let's see how it works. For each point, DBSCAN defines this epsilon circle, and checks whether it contains this minimum number of points to define to set the core points. Then, so here we found one core point here. After that, we are going to include in the cluster all the directly density reachable points in the cluster. After that, we are going to include in the cluster all the density reachable points that are connected to the core point via some chain of directly density reachable points. And then after that, we are going to add more of these directly density reachable points, including the border points, and then some more. And then at this point, we cannot add any more points. We don't find any points that fall in any of the circles built around any of the points in the cluster. So we have to stop. The cluster is complete. So for the remaining data, we start with a new point. If you see here, there is the green point, that's the new core point, and we are going to start this process of adding directly and density reachable points to the cluster, again for this new green cluster. So this is how this DBSCAN algorithm works. So the DBSCAN algorithm uses spatial index structures, and it's quite complex. It's computationally quite complex. So it's actually a relatively slow algorithm to implement, especially if you have a lot of data. The nice thing of the DBSCAN is that in theory, it can build also clusters with non-spherical shapes. So you can have also concave, non-convex shapes for your clusters. And then, of course, the two parameters that you need to define at the beginning of the DBSCAN procedure is this radius for the core points, epsilon, and the minimum number of neighbors that you need to have in a circle to make that a core point. The node that implements the DBSCAN algorithm is called DBSCAN, and then here you can see that some of these clustering nodes, they have an extra input port, this gray input port, where you can define the kind of distance that you want to use for that particular algorithm. And then, of course, as I said before, the different distances are going to give you different cluster partitions. And those are some of the clusters that the DBSCAN algorithm can find. So those are just spherical clusters, but then you can see here, you can find much more complex shapes of the cluster partitions, and here as well. Okay, so the customer segmentation is one of the case studies where you can use, it's one of the case studies when you can use the clustering algorithm. If you know what you are doing, the goal of the customer segmentation is to have your customers on one side, and then you want to put them in some buckets. So for example, if you have a campaign, you might want to address them by age, and then you might want to separate them by age. So young, less young, middle age, and maybe older people. So if you know what you're doing, you can build a rule system, and then you can define the customer segmentation based on the rule system. If you don't know what you are doing, which is often the case, then in this case, you can use one of these clustering algorithms. And then in this case, you can have the, you can use one of these clustering algorithms, and then you can have the clusters at the end. And in theory, all the similar customers end up in the same cluster, and that can help you define the groups of customers that you have. So customer segmentation is a classic problem when clustering is used. This is the customer segmentation workflow. I don't know if you remember the workflows that Kathrin has shown you before. You had the data reading here. You had a bunch of yellow nodes. The yellow nodes are for the data preprocessing to prepare the data. And then you had in green the algorithm. So as you see, the structure is pretty much the same as what she had. Data reading, data processing. And then here, instead of having the decision tree or the random forest like she had, we have the k-means algorithm. Remember that we performed the normalization before applying the k-means algorithm. And then, of course, if we want to visualize the clusters and the results of the k-means algorithm, we need to denormalize the data here, for example. So we denormalize the data, and then here there are some visualization of the final clusters. What I wanted to make you notice is that there is no scorer node here, of course, because it's an unsupervised procedure. We don't have the golden truth that the model has to learn, so we cannot tell how well the model has implemented the original task. One of the things that we can tell, though, is give some measures of of the quality of the implemented cluster. So, of course, we said at the beginning that the clustering procedure has to put together the most similar data points and put in separate clusters the most different points. So the silhouette coefficient here is one of the measures that allow you to measure how well the most similar points have been put together and the most dissimilar points have been separated. But that's just a measure of the quality of the clustering. Doesn't mean it doesn't tell us if it's correct or not. There is no correct or wrong in clustering. So another algorithm that I want to talk about today is the recommendation engines, and this one will be the last algorithm for the day. So, you know, when you go to an e-commerce website and they tell you the people who bought this item, they also frequently bought this other item. So, and then they make you a recommendation about this new item. So those are the recommendation engine, and they use two main algorithms. One is the collaborative filtering and one is the a priori algorithm. I'm going to talk here about the a priori algorithm, and then maybe if you're interested, you can check what the collaborative filtering does. So the market basket analysis or recommendation engines, there are two different names for the same thing, is based on the a priori algorithm. The a priori algorithm is based on the analysis of many shopping baskets. You have many customers coming to your e-commerce site or your supermarket or your bookstore. They come, they fill a basket, they buy something. You have many of these baskets from your many customers, and then you just analyze the content of these baskets. Based on the content of these baskets, you realize that when people buy milk and diapers, often they also buy beer. So what do? If somebody comes into your bookstore or into your supermarket and they buy milk and diapers, you recommend to buy the beer. And that's pretty much how the recommendation engines work. So let's see how the a priori algorithm works. The association rule that you want to define a set of association rules, of recommendation rules. The association rule, classic, has this kind of form. There is an if and an antecedent, and then there is a then and then the consequent. The consequent is the recommendation. The antecedent is what you already have in your basket. So it's going to have any kind of association rule that you want to define is going to have this kind of shape. If product 1, product 2, then recommend product 3. Okay, so let's see how we do that. We have n shopping baskets, n can be so hopefully many. We take all the contents of the shopping baskets. We do some search of the most frequent item sets, so the most frequent items that come together in a basket, and that's the sorted item set by frequency. So we have, for example, that H and F often come together, A and C often come together, A and B, and up to A, B, F, and H also often come together. So based on these frequently found item sets in basket, I can define some rules. So I can say that, let's consider, for example, A, B, F, and H products, they come together. Then I can define the following rules. If the customer has already A, B, and F in the basket, recommend H. If it has A, B, and H in the customer, recommend F, and so on, right? Now, from one frequently found item set with 4 items, I can define at least 4 rules, but probably more, because of course I can consider also when the customer has in the basket only A or B or F. So which one shall I choose? I mean, I can generate many rules from that item set. Which one shall I choose? So each association rule comes with a few measures of reliability. So let's suppose we consider this rule, this possible association rule. Then there is the definition of the item set support, S. So the item set support tells us how often these items have been found together. So how many baskets contain these 4 items with respect to all the baskets. Of course, if I have only one basket out of 2,000 that contain these 4 items together, then of course it doesn't happen that often. Then maybe the rule is not that you know, I cannot rely on that much to make a recommendation. The next measure is the rule confidence. So here we measure how often the antecedent is found together with the consequent. So we measure how often the 4 items are found together and how often the 3 items of the antecedent are also found together. Of course, even here, if we have only one case that A, B, F actually are found together with also H, then maybe it's not something I want to recommend. And then the last one is the rule lift. The rule lift wants to measure how often the antecedent and the consequent happen together compared to happening by random chance. And then here we measure the support of the rule by with respect to the support of the antecedent and the support of the consequent. So the rules which have the highest support, confidence, and lift, those are the most reliable rules, and those are the ones that I want to use for my recommendation engine. So what happens is that when you do the when you find the most frequent item sets in all these shopping baskets, you end up with, let's say, 200 rules. Then you extract only the top 20 or top 10 or top 100, so that, I mean, the non-important rules or the rare rules, the ones that never happen, they are not considered to make recommendations. There is one note that there are 2 notes that implement the association rule mining. One is the association rule learner and one is the association rule learner Borgelt. They implement exactly the same algorithm, only that the association rule learner Borgelt has it's optimized for speed. So what this node does, discover all the frequent and strong association rules of the type if product X, then recommend product Y. So those are the rules that have sufficient support and confidence. When you do the training, you use the association rule learner to build the association rules. When you have a new customer coming in with a shopping basket of A, B, and C, you use the subset matcher to compare the content of the customer's basket with one of the antecedents of the association rules, and then once you find the match, you perform the recommendation. So the whole association rule, the whole training phase of building association rules consists of 2 steps. In the first step, we find all the frequent item sets, and the item sets that happen with the highest frequency, and in the second step, you find the strong association rules, so the ones that have the highest confidence, so the highest measured confidence. So this is the part, the one that finds the most frequent item sets that includes the most computational, the highest computational complexity, and is the slowest one. So those are the 2 parameters, it's minimum support and minimum confidence to decide to adopt an association rule for the recommendation. Okay, so let's have a look at how this would work. Let's consider the association rule that I've shown you before. If milk and diaper, then beer, right? So let's see how often those are found together across all the shopping baskets, and how often they are found together containing, so how many baskets are found containing these antecedents. Okay, so let's have a look. Let's calculate the support. The support is the frequency of the number of baskets, including milk, diaper, and beer. This is our data set, a tiny, tiny one. It's just a toy data set. We want to find the milk, diaper, and beer contained, all the 3 items contained in this data set. So that defines the support with respect to all the shopping baskets that we have. So it's 2 times out of 5 shopping baskets, and 0.4 is the support. Then we have the confidence. The confidence is the number of times that I find all 3 items divided by the number of times that I find only the antecedent, so the milk and diaper. In this case, it's 2 times out of 3. So the confidence is 0.67. And now the next one is the lift. And then here we have the support for the milk and diaper alone, the support for the beer alone, and then the support for the milk, diaper, and beer together. And then in this case, we end up with this value here for the rule lift. So this is how the support, confidence, and rule lift work together.